So far, we've seen several different types of hypothesis tests. We've seen the one proportion, the one mean, the two proportions, and the two means. Today, we're going to add another type of hypothesis test into the mix, the goodness of fit test. So let's jump into example one and see what the situation is. A biology professor claims that on average, 15% of her students get an A, 30% get a B, 40% get a C, 10% get a D, and 5% get an F. The grades of a random sample of students were recorded. The following table presents the results. Can you conclude that the grades follow a distribution different from the one claimed by the professor? Okay, what's different about this data compared to the data tables that we've seen in the past? So in the past couple lectures, a typical data table looked like this, right? And what you should notice is that these numbers here in this example, these were cholesterol levels. And these were measurements on 8 different people. And that's not what we have here, right? What we have here, these numbers, these aren't measurements on 5 people, right? These are counts. So these are counting how many people got an A, how many people got a B, how many people got a C, and so on. So they're counting how many people are in each category, right? Which is not what we had before. Before, these were not counts of how many people are in each category. There's no categories. Right, so that's one way to tell the difference between what we're going to do today versus what we did in the past couple of lectures. Okay, so 8 people got an A, right? So the professor claimed that 15% should have gotten an A. So 8 people here got an A. What percent is that? So let's find the total number of people we have here. Let me add up these numbers. Okay, 8 plus 35 plus 49. Plus 15 plus 11. There's 118 people total. 8 people got an A, so 8 out of 118. What percent is that? 8 out of 118 is roughly 0.068. So roughly 6.8% got an A. So notice that if we didn't have B, C, D, and F, right? If those were gone and it was just A, then this is just a one proportion test, right? We would have been asking, is there enough evidence to conclude that the proportion of A's differs from the 15% that's claimed by the professor? But here, we do have these other columns, right? We do have B, C, D, and F. So you can think of a goodness of fit test as a multiple proportion test. Okay, but instead of working with proportions, we're actually going to work with the counts. So I'm going to find the expected counts, what are called the expected counts, which is going to be, if the professor is telling the truth, that 15% gets an A, how many A's should there have been? So how do you find that? Well, it should be 15% of the 118. So 15% times 118, right? I'm going to do 15% as a decimal, which is 0.15, times the 118. Okay, 0.15 times 118, 17.7. And I'm going to do that for all the categories, the B, C, D, and F. B's, there should have been 30% B's. So 30% times 118, which is 0.30 times 118. 0.30 times 118, 35.4. C's, there should have been 40% C's. That's going to be 0.40 times 118, 47.2. D's, 10% should have gotten a D. That's going to be 0.10 times 118, 11.8. F's, 5%. Be careful here. 5% as a decimal is not 0.5, it's 0.05 times 118. 0.05 times 118. 5.9. And this is basically the question now. Is this observed count different from this expected count? So if we look at this, looks like the A's, there's actually 8 A's versus expected 7.7, so there's like too few A's. The B's look okay. The C's look about the same. The D's, 15 versus 11.8, maybe about the same. 11 versus 5.9, maybe there's too many F's in the observed. And the question is the observed row different enough from the expected row for us to actually say that this is different from what the professor is claiming? Okay, so part A, state the null and alternative hypotheses. For a goodness of fit test, I'll start with the H1, right? The H1 is always going to be the same. It's going to be observed. Right? We're asking, is it different from the one claimed by the professor? So we're asking, observed differs from expected, which means the H0, the null, is going to be observed equals expected. Part B, find the critical value and sketch the rejection region. So draw the picture. I'm drawing the same picture that we drew for all the other types of hypothesis tests, but actually for a goodness of fit test, the picture is actually slightly different. I'll put the correct picture up here somewhere, but it doesn't matter, right? I'm going to keep on drawing the same picture that we drew for the all the previous hypothesis tests. Now, the first difference is for a goodness of fit test, even though it says not equals, it's always going to be shaded to the right. And I'll explain why it's always shaded to the right a little bit later. Okay. Even though it's not equals, it's shaded to the right. On all the other hypothesis tests we've talked about, not equals is actually two tails. The second difference is in the other hypothesis test, we were either looking for a Z star or a T star. For a goodness of fit test, we're actually looking for another thing that's called chi-square. So I'll call it chi-square star, which is why a goodness of fit test is sometimes called a chi-square test. The word chi is the Greek letter chi, and then square just means we're going to square it. So we're going to look for a chi-square star, not a T star or a Z star, a chi-square star. And then just as before, the alpha 0.02 is the shaded area here. So our alpha here is 0.02, which refers to the shaded area. And what we're looking for here is this is really just a area to chi-square problem. So going back to our formulas, I can now talk about this last formula here. So this is going to be for the chi-square test. And for part B, we're actually going to go area to chi-square. For the chi-square situation is this last row. Area to chi-square. For the chi-square situation is going to be Q chi-square left area df. All right, so we're going to do Q chi-square left area df. Left area. 0.02 is the shaded area to the right. I want the other side. So I'm going to do 1 minus. One minus 0.02 I think is 0.98. And then Q chi-square has a df. So this df has nothing to do with the sample size. It has to do with the number of categories. Okay, it's one less than the number of categories. We have 1, 2, 3, 4, 5 categories, right? A, B, C, D, F. 5 categories, one less than that would be 4. Let me write that here. So this is the number of categories minus 1. So in R, we're going to do q chi-square 0.98 comma 4. And just based on my picture, I expect a positive answer. So if you get a negative answer, you probably just forgot to do the 1 minus on the alpha. So just remove the negative sign. Okay, so in R, we're going to go q chi-square 0.98 comma 4. Okay, I do have a positive answer here, so that's 11.668. Okay, and that's a chi-square star. Part C, find the test statistic. So we're going to be using this formula for the chi-square test to find the test statistic. So for this, I need to switch over to Google Sheets and enter this data. All right, here I am in Google Sheets, and what I'm going to type in is I'm going to enter in the observed numbers and the expected numbers as columns. So I have my observed, and then I have my expected numbers. My observed numbers were 8, 35, 49, 15, and 11. My expected numbers, which we calculated, were 17.7, 35.4, 47.2, 11.8, and 5.9. And what I need to do to calculate is, if I look at my formula sheet, I need to set this up. So what this is telling me to do is O is observed, E is expected. So I need to take my observed minus my expected squared divided by expected, and then add up all those numbers. So I need to create a third column where I calculate this part, the O minus E squared over E. All right, so let's go back. I need a third column, and I'm just going to write out that formula. You don't have to. So it's parentheses observed, so O minus E close parentheses square. So square is the up caret, which is the symbol above your 6, 2, and divided by expected E. Okay, I'm going to set up the first box here. So to get Google Sheets to do any calculation for you, you need to start off with an equals. So equals parentheses, and then I want to do O minus E. So instead of typing stuff in, I'm going to click on observed, which is the 8, minus, click on the expected, which is the 17.7, close parentheses, square it, which is the up caret 2, divided by expected, click on the 17.7, and hit enter. Okay, there should be a autofill. You can use the autofill, or if you don't use the autofill, you can just click on the first box and then move your cursor to the bottom right until you see a plus sign, and then click and drag. So all we're doing here is we're copying the first box into all of the other boxes. So we're just copying the directions that we gave Google Sheets into the other boxes. All right, and then all we need to do is add up that last column. So to add up that last column, equals SUM, sum, parentheses, and then highlight that last column. And that's our chi-square test statistic. All right, so let me go back and write that down. The test statistic that we found was chi-square. It was 10.665. That's rounded to 3 decimal places. Part D, draw your picture. Should be the same picture that you drew in part B. For a chi-square, it's always going to be shaded to the right. Put your test statistic that you found in part C on your picture. And then your job is to find that shaded area. Okay, this is really a chi-square to area problem. Chi-square to area. Chi-square to area for the chi-square situation is going to be p chi-square df. So we're going to do p chi-square the chi-square, which is 10.665, comma df. df, remember, is number of categories minus 1. There were 5 categories. Minus 1 is going to be 4. So in R, we're going to do p chi-square (10.665, comma 4). 0.969. That seems big. That can't be right. And that's because just like the p-norm and pt, p chi-square always is going to give you the left area. So that's the left unshaded part. That's not what we're looking for. We're looking for the right area. To find the other side, you have to do a 1 minus. So we'll do a 1 minus. So 1 minus 0.969. 0.031. That's the area, the shaded area, which is the p-value. And then the rest of this is the same as all the other ones. Part E, reject or don't reject the null. Look at your p-value and compare it to your alpha. Our p-value is 0.031. Our alpha is 0.02. Okay, if you need to, add some zeros so that they both have the same number of decimal places. This one has 3, this one has 2. Let me add on a 0. You're really comparing 31 versus 20. So it's not less. If it's not less, you don't reject. And then the sentence, the same. State your significance level at alpha equals 0.02. Level of significance, there is or is not, because we did not reject. There is not enough evidence. To conclude that, and then go back to our question, can you conclude that the grades follow a distribution different from the one claimed by the professor? So there is not enough evidence to conclude that the grades follow a distribution different from the one claimed by the professor. Let's talk about why, even though it's not equals, why for a chi-square test, it's always going to be shaded to the right. And it comes from the test statistic. So when we calculate the test statistic for the other hypothesis test, right, we were using one of these 4 formulas, the 1 proportion, 1 mean, 2 proportions, or 2 means. And if you remember, you could have gotten a positive answer and you could have gotten a negative answer. So sometimes you got positive answers and sometimes you got negative answers. Which is why when we talk about differs or not equals, you could be not equals on the positive side or you could be not equals on the negative side. Which is why we had to take into account both of those possibilities, and that's why the picture was two-tailed. For the chi-square situation, this test statistic is never going to be negative. If you look at the formula, we're doing observed minus expected, and then we're squaring it. Anytime you square something, you always get 0 or positive, and then you're dividing by expected. And expected is just these counts, which are going to be positive anyway. So the test statistic for a chi-square is never going to be negative. So there's not a possibility of us being not equals on the negative side, which is why we don't consider the negative side, and it's only going to be shaded to the right. Example 2. Following are the total number of absences on each day of the week for a statistics class during the spring 2021 semester. Okay. Notice that this is going to be a chi-square situation because the data here represents counts of how many people are in each category. So this is how many people were absent on a Monday, how many people were absent on a Tuesday, and so on. Okay, this is definitely going to be a chi-square situation. What's different about example 2 compared to example 1? In example 1, I gave you percentages so that you can calculate the expected. Here, I'm not giving you those percentages. So what do you do? Well, let's first Let's first find the total because we need that anyway. Total number of people, 39 plus 24. Plus 20, plus 26, plus 41. 150 total. Now, if you're not given percentages for computing the expected, okay, this first row here is the observed. If you're not given the percentages to compute the expected, we're just going to assume that we're going to split this evenly among all the categories. So there's 150 total, and there are 1, 2, 3, 4, 5 categories, so divide it evenly. So 150 divided by 2, 3, 4, 5, by 5. 150 divided by 5 is 30. So there's going to be 30 in each category. The expected, if you add them up, it should equal the total. Okay, part A, state the null and alternative hypotheses. H1 is going to be observed not equals expected. It's always going to be not equals for a goodness of fit test. H0, observed equals expected. Part B, draw a picture. Okay, even though it's not equal for a chi-square, it's always going to be shaded to the right. And the shaded area is our alpha. Our alpha here is 0.02. And then we're looking for chi-square star. Okay, this is really a area to chi-square star situation. Area to chi-square star. Area to chi-square star for chi-square situation is q chi-square left area df. So q chi-square left area of this picture is not 0.02. 0.02 is the area to the right. I need the other side, so do 1 minus. And I think this is 0.98. df, okay, df is not having to do with, doesn't have to do with the sample sizes for this chi-square situation. It's number of categories minus 1. Number of categories, 1, 2, 3, 4, 5, minus 1, 4. So we're going to do q chi-square 0.98, comma 4. Which is actually the same as the other one. Q chi-square 0.98, comma 4. So we should get the same answer, 11.668. Part C, find the test statistic. So I need to enter this data into Google Sheets. All right, we're back in Google Sheets. I'm going to enter my observed row and my expected row as columns. Let me do that over here. Observed, expected. My observed were 39, 24, 20, 26, and 41. My expected are all 30s. And then I need to do the third column. So the third column is going to be parentheses observed minus expected, close parentheses square, which is the up caret, the symbol above your 6, 2, divided by expected. And I'm going to set up the first box. So first box is going to start off with equals. Anytime you want Google Sheets to do any calculations for you. Equals, parentheses, observed, click on the observed, which is the 39, minus expected, click on the expected, which is the first 30, close parentheses square, up caret 2, divided by expected, click on the first 30. And hit enter. You can use the autofill, it's correct, or you can move your cursor on the first box to the bottom right until you see a plus sign, and then you can click and drag it. And then all you need to do is add up that last column. To add up the column, you're going to do equals sum, S-U-M, parentheses, and then highlight that last column. And then we'll copy down that answer. The test statistic that we found was 11.8. Part D, draw your picture. Chi-square is always going to be shaded to the right. Put your test statistic on your picture. And your job here is to find the shaded area, that's the p-value. This is a chi-square to area problem. Chi-square to area. Chi-square to area for the chi-square situation is going to be a p chi-square df. So p chi-square. Our chi-square was 11.8. df should be the same as in part B. Number of categories, minus 1. So number of categories was 5, minus 1 is 4. P chi-square 11.8, comma 4. .981. Okay, that can't be right. I'm expecting a small answer here, and that's because p chi-square gives you the left area, which is this left unshaded part. I'm looking for the right area, which means I have to do 1 minus. So 1 minus 0.981. .019. Part E, reject or don't reject. So take your p-value, compare it, and see if it's less than the alpha. Our p-value is 0.019. Our alpha, 0.02. Okay, if you need to, add zeros so that it matches the number of decimal places. This one has 3, so let me add on a 0 to the alpha. This is really just 19 versus 20. It is less, so if it's less, you are going to reject. And then finally the sentence at state your significance level at alpha equals 0.02. Level of significance there is or is not, because we did reject, there is enough evidence to conclude that, what are we trying to conclude? Conclude that the absences are more likely on some days of the week than others. That the absences spelled that wrong. Absences. Whatever. Absences are more likely some days of the week than others. And that's the goodness of fit test, or the chi-square test. Have a good day. I'll see you in the next one.